Hello everybody, we are back and we are going to keep plugging away in Chapter 8 today. And last time I left off talking about some stereochemical requirements in E2 reactions. We said that you had to have something called an anti-paraplanar arrangement of your beta hydrogen and your halogen. Alright, and we saw a particular application of that in linear molecules. There's going to be another important application of this, and this is going to be within cyclohexanes, right? So you remember cyclohexanes, right? That's the hexagon. Do. All right. So if we have an alkyl halide that's part of a cyclohexane ring, it's not quite as easy as just looking at it, taking away the halogen and a beta hydrogen and making a double bond. That's because we have to have this anti-paraplanar arrangement. And with cyclohexanes, that means we have to look at it very specifically through a lens that is going to be a little familiar and perhaps a little bit scary to you. That's our friends, the good old chair conformations. Woo! Chair conformations. Boy, howdy. All right, let me draw this in a chair conformation. All right. So let's say we had this. All right. And you know, on either side we have two beta carbons here and here. They're identical though, so they really only count as one type of beta carbon with one type of beta hydrogen. I'm just going to pick this one to work with over here. Okay. All right. So we have to have an anti-paraplanar arrangement. What does that mean as far as chair conformations? Here's what it means. You need your both your halogen, chlorine, bromine, iodide, whatever you got, and your beta hydrogen to be axial. That is an absolute requirement. If they're not both axial, then you can't have an elimination. All right. If you look at this, we've actually learned that this can exist in a couple of different conformations. We have this one, and then we have the flipped conformation, the chair flip. And I drew the wrong pair of arrows there. How embarrassing. If we do a ring flip, remember, everything axial goes equatorial and vice versa. So it would look something like this. Okay? And remember, these two forms constantly exist. They interconvert between each other. They reach an equilibrium. All right? Now, when can you get an E2 reaction? Well, we have to have the axial arrangement of both the halogen and the beta hydrogen. If you look at this one over here, where's your Cl? Right, it's equatorial. So, can this one be involved in an E2 dehydrohalogenation? No, it can't. All right. So, whenever we're trying to figure out, what type of products that we would get when working one of these, we always have to work off the arrangements, only the arrangements that have what we need, right? Axial arrangements of both your halogen and your beta hydrogen. All right. If you look over here in the other one, we have an axial halogen right there. If we look at our beta hydrogens, this carbon has two of them. One of them is equatorial, which is no good, but one of them is axial. So this particular one that I've circled can be eliminated. And you can end up forming a double bond between these two carbons. And if you translate that to the hexagon structure, it just looks like that. Okay? Not too bad, right? All right, let's take a look at another one. Let's take a look at a dye-substituted species. And you can see it gets a little bit more complex. as far as determining what you're actually going to get. Let's try this one. All right, and this one's going to be a little bit more complex for a couple of different reasons. First off, we have two substituents on here, right? Cl and a methyl. We know when we have a di-substituted cyclohexane ring, we can have either cis or trans, right? And so when we draw the chair conformations, we have to account for each one of those, right? So the first thing I would do say we're doing an E2 reaction. First thing I would do is I would just go ahead and draw the different chair conformers to see which ones are going to work, which ones are possible. All right, so if we do this, all right, there's our Cl and H on that carbon. All right, and on an adjacent carbon, a beta carbon, we have a methyl group, and we have an H. All right, so since this is cis, that means both the Cl and the CH3 need to be pointed in the same direction. So I'm going to put that CH3 group right there, put an H right there. Okay. Then we have the ring flipped version. Hopefully by now you have an idea of how to do this. If not, let me know. It's going to look like that. Okay? All right, so let's figure out what's going on in the cis version before we move on to the trans. First of all, can we eliminate anything here? I think you can. Again, we need an anti-paraplanar arrangement of beta hydrogen and Cl. They both have to be axial. In this guy, we have an equatorial Cl. So we know automatically that that's not going to work. All right, so we're not even going to bother with that one. We're just going to work off of this guy. Okay? Now, if you look over here, we have a Cl, axial. We have a beta hydrogen, axial, right? We can get an elimination there. Absolutely. Double bond between those carbons. And you still have a CH3 right there. So if we wanted to translate that to a hexagon, it would look like that. And that would be a product. All right? Hopefully that makes sense. Here's a little catcher, though. We're not done. There's still more we can actually do with this one. Why do you think that is? Take a second to think about it. Hey, guess what? We have a different beta carbon that we can work with as well. Don't forget, we got this guy over here. That's also beta. And since this one does not have a methyl group, that means this one is different from this one. So we have to take into account any beta hydrogens that might be sitting right there as well. All right? So what I'm going to do is I'm going to redraw this now that I've marked all over the other one. I'm just going to draw the axial CH3 here just to save a little room because it does get a little messy. All right, and I'm going to draw the hydrogens on the other beta carbon. And if you look here, we have an axial H right over here that goes along with our axial Cl. So you can get elimination and formation of a double bond between those two carbons as well. Get it right there. You can get it right there. I said that really softly because I forgot I was talking to the iPad, so I almost went conversational there, so please forgive me if I get too soft or loud at any given point. And if we translate this to the hexagon, we get this. When those are two distinct alkene products. All right, so working off the cis version gives us those two. Okay? All right, well, let's see what happens when we work with the trans. All right, so for the trans, again, I'm just going to start off this way. Cl up there, up there. Now, if this is trans, we want the methyl and the chloro to be pointing in opposite directions, right? So that means if we have an axial Cl, we have an axial CH3, and we have an H there. And then we can, of course, draw the ring flip. Which looks like that. All right. Well, can we eliminate anything? You bet we can. Well, again, we know we have an equatorial Cl. We know that's not going to work, right? So we're just going to forget about that altogether. And we're going to focus on this one. All right. All right, well, let's look at the beta carbon right over here, the one that has the methyl group. What do you think we can do with that? All right, what are we looking for? Well, again, we're looking for beta hydrogens. It does have a beta hydrogen right over here. But if you look at it closely, you'll see that it's in the wrong position. We need that beta hydrogen also to be axial as well. So that means you're unable to get an elimination between these two carbons. The carbon with the Cl and then this carbon with the equatorial beta hydrogen. All right? That's a little different than the last one, right? When we looked at the cis versions, we saw we could make a double bond there. Can we do anything? Well, don't forget, there's another beta carbon. This beta carbon has two H's, and lo and behold, one of them is on an axial H. So, what that means is that you can absolutely make a double bond between those two carbons. And if you translate it to the hexagon, it's going to look like that. Okay? So you see, both the cis and the trans can make this product right over here. Only the cis can make this product. So, you can infer some information about this. First of all, if you happen to isolate the cis and the trans versions of these rings before reaction, you could isolate either just one or two products, depending on which one you perform the elimination with. If you had a mixture of cis and trans and you did this reaction, you could probably make an accurate prediction that this one might be present in a little bit higher amounts, just because stereochemically it's going to be favored. Okay? So, bottom line, whenever you're doing these E2 reactions with chair conformations, make sure you have axial beta hydrogens and axial halides, and then make the according predictions. All right. That is it for E2 reactions for the moment. We'll come back to those a little bit later. Now let's talk about E1s. All right. So again, just like anything else, there's certain little features of E1 reactions that we can look at, and also certain preferences. All right. Let's take a look at an example here. Let's say you had something like this. All right. Typically, what you do is you have a alkyl halide. You have a base of some sort that has an unshared pair of electrons. Usually this base does not have a negative charge. Usually it's neutral. All right. You're going to see that there's a lot of similarities between the E1 reactions and the SN1 reactions. The first thing to realize about this is that E1 reactions, I'm going to draw this down here, are multi-step. Why? Because just like with SN1 reactions, they always go through formation of a carbocation. So if you're looking at this, the first step is exactly the same. The leaving group is going to leave. And it's going to produce a carbocation. Okay? Alright, then the base is going to come in and it's going to target a beta hydrogen. Now we actually have 3 different beta carbons here, but they're all identical to each other, and they all have identical beta hydrogens, so I'm just going to pick one. I'll just put one right there. Your base is going to come in, grab that beta hydrogen, and then these electrons will swoop into a double bond, and viola, you have your alkene. You also get couple of byproducts here that I should mention as well. Okay? So multi-step, formation of the carbocation, then in the second step you pluck off your H and make your double bond. Alright, if we wanted to look at a real world example of this, yeah, typically what we might do is we might have something like, this again. Base. Honestly, the most commonly used bases for E2 reactions are either going to be water, or alcohols, or ammonia, which is NH3. Although there are some others. Look in your book. They'll have some suggested bases. All right. So the way this proceeds is that you lose the Cl. Get your carbocation. Water comes in, grabs that H. Electrons make a double bond, and boom, you have your product. All right. Now, you may be thinking to yourselves, wait just a cotton-picking minute. This looks awfully familiar. Haven't we seen a tertiary alkyl halide in a reaction with water before and it did something totally different? You would be absolutely correct. That is a thing that happens. I will explain that in just a minute, so don't fret. So, it's not your imagination. That is actually a thing. Alright. But before I get to that, I want to mention just a couple of other things. One or two other things. Number one, this is an E1 reaction. What do you think the 1 stands for? Well, just like it did with SN1, right? It's a first-order reaction. We saw we had a couple of steps. First, we had formation of the carbocation, and then in the second step, we took away our beta hydrogen and simultaneously made our double bond. All right. Remember, whenever you're writing a rate expression, a rate law, this rate equals K, and then you include all reagents that are involved in the rate determining step. Right? Since we have 2 steps here, one of them's going to be slow, one of them's going to be fast. Just like with SN1 reactions, the formation of the carbocation is going to be far and away the slowest step. All right? And so what is the only thing involved in that slowest step? It's your alkyl halide. So that's why E1 reactions are first order. All right? It's also useful to be able to recognize what transition states you're drawing. Right? For E2, excuse me, for E1 reactions, you're going to have 2 transition states, right? Because you have 2 steps. Well, in the first step, you're actually making your carbocation, right? The leaving group is in the middle of leaving, so you're going to show that by drawing that CCl bond breaking. Cl is in the process of becoming negative. carbons in the process of becoming positive. Okay? I keep putting in like these awkward pauses in here, just like I would do in class whenever I'm like getting ready to ask you guys a question. Good grief, I really need to get you guys in person. This is driving me crazy. I like making the videos and all, but I really, really enjoy teaching in person. I hope COVID has some mercy on us next semester and we get to do this in person more often. Anyways, sorry, that aside is over now, so let's get back to business. What's happening in the second transition state? Well, second step, we're in the middle of breaking off a beta hydrogen, and we're in the middle of forming a double bond. All right, so let's see how that works out. So, we're in the middle of breaking off this hydrogen using our base, which in this case is water. All right, and we're also in the middle of forming a double bond there. All right. Partial charges. This carbon right here was positive. It's in the process of going to neutrality, so it's going to have a partial positive. This oxygen was neutral. It's in the process of gaining a proton and going positive, so it's going to also get a partial positive. And there you go. There are your two transition states for this reaction. All right. Okay. All right, so there's a couple of little, quirks of, or not quirks really, but traits of E1 reactions. Let's talk about the preferences. All right. Again, just like any of the other mechanisms from the last two chapters, we look at three things in order of importance. First is the type of alkyl halide. All right. Now, what did you remember seeing for SN1 reactions? Think about that for a second. Right? If you remember, on SN1 reactions, we saw that the preference was tertiary, followed by secondary, and then for pretty much all intents and purposes, methyls and primaries don't react. That's exactly the trend that you see here. Tertiaries are favored, secondaries work okay, and for all intents and purposes, primaries are non-reactive. Okay, so this has the same preferences as far as alkyl halides that you see in SN1. Type of base that's used. These work with weak bases. Examples: water, alcohols, ammonia, amines, and a few others. All of them neutral, but all of them have unshared pairs of electrons that are available to act as bases. Solvent, just like we saw with SN1, they work with polar protic solvents. Okay? So, and much like we saw with SN1 reactions, oftentimes, in fact, most of the time, your base and the solvent are the same. Okay? All right. So there are the there's the properties of E1 reactions. All right, now I told you that, or previously, we looked at the setup for that sample E1 reaction, and I told you it looked pretty familiar, right? And hopefully you guys caught that. You guys saw pretty much the same type of setups when we talked about SN1 reactions. That is going to lead to a lovely little bit of complexity that will probably drive you crazy, but it's unavoidable. for dehydrohalogenations, actually, let me back this up. I don't want to say dehydrohalogenations. I'm rephrasing. In alkyl halides, you always get SN1 mechanisms and E1 mechanisms mixed together. You cannot have an SN1 reaction without also getting competing E1 reactions, and vice versa, of course. This is only for alkyl halides. I want to emphasize that. Next chapter, we're going to look at alcohols. We're going to see that we can also have SN1 E1 reactions, but we can keep those separate. But for these, we can't. Why? Because the set of conditions that favor each is identical. They like the same things. So, going back to that one we just did, we put this tertiary alkyl halide in with water. We saw it just then that, yeah, we can get this elimination product. But at the same time, it is also possible to get the nucleophilic substitution product as well, the SN1 product. And you do. You get both of them. So you get a mixture of E1 and SN1. That's why if you're an organic chemist and you're trying to make something in the lab by an elimination or a substitution of an alkyl halide, you want to avoid the first order mechanisms if at all possible, because number one, you're not going to get a good yield. It's always going to be mixed up with the other one. And number two, you got to do extra work to try to separate those products out. So, yeah, organic chemists in the lab, when working with alkyl halides, greatly prefer E2 and SN2 reactions. Sometimes it's not possible, though. And in that case, you're always going to get a mixture. This is a nice, always hard and fast rule. So, if you see that setup, be prepared to show that you can get both sets of products. Okay, I'm actually going to cut this video off here, just because I don't know how long it's getting, and I don't want to get too long with it. And I'm going to make another video that is going to sort of take all four mechanisms into account, into a giant witch's brew, and we're going to see what comes out of it. All right, until then, have a good one.